So see, let's start. So transfer of heat. Okay, when I say transfer of heat, right? Okay, I basically mean what? I basically mean how heat energy can be transferred. Okay, and that transfer can take place between solids and liquids, or liquid and gases, or from solid to a gas also. Okay, so there are three modes, we call it, three methods or three ways heat can be transferred. Okay, so the first one is conduction, and very common one. Convection is also very common, and even radiation is very common. Okay, so these are the three methods. Let me talk about them one by one. Okay, see, 1 second. Yeah, so yeah, so see, okay, what is conduction? See, if I tell you, okay, I have a container, or any solid. I have any solid, okay, and you know what, I take another solid, or let's say this solid is very at high temperature, no, the temperature of this solid is very high. Okay, what happens if I take another solid and keep in contact with this first solid, guys? What will happen? What do you think? Will the second solid also conduct heat or not?
Yes, sir.
Yeah, the second solid will also conduct heat. Okay, and if you notice what is happening, you know, there's a contact, right? There's a contact between what? Solid number 1 and which one? Solid number 2. There's actual contact between them. Okay, this contact helps in transferring heat from one body to which body? To another body. Okay, and this is also true. Okay, if I just take a single object also, and if I have some source of heat here, okay, then automatically what will happen? This face of the solid will become hot first, and automatically what will happen? Heat will just stay in this face, or it will be transferred to the other faces also?
Transfer to the other.
Yeah, transfer to the other faces also. Okay, and if you notice, all these faces are in contact. Okay, they are in contact, right? So this is what we call is conduction, no, to conduct directly using contact. Okay, conduction is basically has to do with contact, of course, and this is the most this is the way. Okay, this is how solids, they do what? They conduct heat, mostly seen in what? Mostly seen in solids. Okay, so can you understand this one, guys? The first process, the conduction process.
Yes, sir.
Okay, okay.
Yes, sir.
I think this is quite
Yes,
okay.
sir.
Okay, then let me just show you what happens to solids. Okay, when you give heat, or when they receive more and more heat. Okay, so basically this is the picture. We have a solid, then we have atoms or molecules arranged in the solid. They have some spacing between them. Okay, and I think you know by now, right? These atoms or molecules, right, that I've drawn. Okay, what do you think? They are at a stationary state, or they keep on vibrating?
Vibrating.
They keep on vibrating. The molecules or the atoms, right, they keep on going back and forth like that. Okay, and what they do, they collide with other atoms nearby. Okay, that is how heat is transferred. Okay, so suppose I tell you, okay, if I increase the temperature, what happens? If I increase the temperature, the same molecules that I'm talking about, okay, they vibrate with more what? More amplitude. Yeah, more amplitude. Okay, so when they vibrate with more and more amplitude, okay, slowly what happens? This chain, right, will proceed and proceed. If the energy is gained from this direction, right, they are going to start vibrating. The other side of the molecules or the atoms, they start vibrating more and more, and this is how you conduct heat. Okay, so even if I touch, okay, with my fingers, no, this is my fingers. Okay, I touch this, what will happen? These vibrations will be picked up by what? My fingers, the molecules in my fingers. Okay, even the molecules in my fingers, they will start vibrating with more amplitude, and my fingers will become hot and hot and hot. Okay, I think you understand the process. Okay, then any idea about oh yeah, one more let's read quickly about these points. So in conduction, right, the transfer of heat, what do you think? It can be in one direction or any direction? Means
So one direction.
no, what I mean is, if okay, do you think it will be in one direction, or it can be in any direction?
Any direction, sir.
Any direction, no?
direction.
Because vibrations will be picked up in all directions. Okay, not only in one direction, no. So that is what they called it. Okay, but this process is what? Very slow. I think you can make out why. Can you understand why it's a slow process? Because if I start conducting from one phase, right, then what will happen? Automatically you'll get the other phase also very much heated up at the same time, or it will take time for the heat to reach to the other end?
It will take time, sir.
It will take time. So that's why we call it a slow process. Okay, not a very fast process, but a slow process. Yes, yes. Okay, then Giovanna is there. Giovanna has joined. No, Giovanna is writing no more recording because I don't want to record. You know why? Because you guys know are becoming lazy, huh? You will say, sir will record, so I'll not join the live classes, and then you lose interest. Okay, what is going on? And last time, you know what happened? The second part, no, half of them was recorded and half of them it did not record. The last class, exactly the last class. Today the new student has joined. Demaya is there, no? You joined, but yeah, she's there. Okay, Demaya, can you hear me?
Yes, sir.
Yes, yes. Demaya, see, okay, your school, I think they have not reached this topic, no?
So no, sir.
No.
We haven't done this yet.
You haven't done this yet, okay? So, check, okay? But these things are there for the finals, no? That's why I'm doing, okay? So, other things too, I've already completed. Okay, so just check, okay? Yeah, see. Okay, what is the next process, guys? The next process is what? How can heat be transferred?
Convection.
Convection. Oh, Ptolemy has also joined. Ptolemy, I thought you are in vacation. No, not yet. I mean, say you're done with vacations. Ptolemy.
Yes, sir.
Okay. See, okay. Convection is a process whereby the molecules, okay, they actually move around. Okay, in solids, what do you think? The molecules are actually leaving their position. They are not leaving their position, guys. Here, they are
Not
transferring.
leaving.
They are not leaving. They are just vibrating more and more, but they continue to remain in their mean position. This is the mean position. This atom or molecule will vibrate, but it will not leave its mean position, right? But let's check this liquids and gases. Okay, this is a liquid. Suppose, okay, and you tell me now, if I have this liquid molecules, right, and then when I heat them, heat from the base, okay, here, like that, okay, what do you think is going to happen to these molecules? They stay there or they start moving, or they move now in different directions, right? What happens? What do you think happens? All these molecules, these are the first molecules, right, which will become hot first, right? They'll become hot first. Now what do they do, guys? They go where? Upwards, or a better word is what? Better way to say is?
Towards the surface.
Much better one will be, they move into a direction, right, where there is heat or less heat. Less heat or less low temperature. Less heat is also bad actually. Where the temperature is high or low?
Low, sir.
Low. Okay, the molecules, right, they are heated up here. They gain temperature. First. These are the molecules present at the base. Because we're heating the base, they gain the temperature first. Then they start moving, okay, in all random directions. That's what liquids do. Even the gases, I think you can understand. Same picture. And then what happens? These molecules, they go up. And the molecules which are at low temperature, right, they go down. Does it make sense? Is it making sense? Just check. Or you can just say, the molecules which are at low temperature, okay, this is a green molecule at low temperature, the red one is a molecule at high temperature. He can go and hit this molecule and transfer his heat there or not?
Yes, sir.
Okay, so now you tell me, the molecules or the atoms in this case, right, they are transferring heat or not? Do you agree they're transferring what? They're transferring heat. Okay, makes sense there. Okay, are the molecules or the atoms maintaining their position, or their position changes?
Position changes.
That means there's a movement of the particles. Okay, same thing happens with gases also. I can show you. Okay, let me take a room. Okay, this is a room, and I want to heat the whole room. I want the whole room to be heated up. What will I do? What should I do? Tell me, guys. I want the whole room to be heated up. I will switch on what?
A heater.
Heater, no? Blower, let's call it air blower. Heater, you know this. Okay, let it be any heater. Okay, so the gases, you know what, the gases, they will fly. See, all these gases, they are continuously flying, like say winter, okay, time, they are flying. They come near this, they take the heat. Now they go to in different directions. Okay, so the heated ones, they now are going to move in the entire room. The cold gases will come, they will pick up the heat, then they'll move in the entire room. Now what do you think, guys? The room is at same temperature, or the room temperature will increase?
Temperature will increase.
Okay, this is the process, right? So what will I call this process? Conduction or convection? Convection. Okay, convection. Why? Because the molecules are actually moving and transferring their heat. Okay, in solids the heat is transferred, the molecules, they do not leave their original position. Okay, One more very okay, let me go back to some points. Okay, so you read these notes later, you will understand yourself. Convection occurs in what? Fluids and actual flow of matter. Okay, this transfer of heat is what going to take place in which direction? Vertically upwards, not left and right much. Okay, it's vertically upwards, and this is much faster. Okay, what is this process? Much more faster compared to what? Conduction. Okay, and yes, we have one more. Okay, one more we have. One is the other one. Tell me, what is that?
Radiation.
Radiation basically, when I say, it means what? Light, right? Light also transfers heat or not? Light is coming from sun. Let's start with that. Not to earth. Do you also agree that heat also is coming or not? Light is coming from sun to earth. Even what is coming? Heat is coming. Okay, and what do you think? We need molecules in between, or we don't need molecules in between for this kind of transfer?
We don't need molecules.
We don't need molecules at all. We don't need atoms at all. We don't need a medium. That's the proper word. Okay, we don't need what, guys? A medium. If I want to transfer heat using what? Light. Light, or let's not call it light, but we call it what? Radiation. Radiation, in other words, means what? Waves. Okay, to be more accurate, have you heard about electromagnetic waves?
Yes, sir.
Okay, give me examples of electromagnetic waves. Let's start with the highest energetic. Gamma, remember this. Okay, the most energetic EMF wave is which one? Gamma rays. Okay, then after that, X-rays. Then we have what? Ultra. You have heard about them. Ultraviolet. Then we have VIBGYOR. VIBGYOR. This is the visible light. They also transfer heat. Okay, all of them, they transfer heat or radiation. They are. Then after red, what do we get, guys? Guess. Infrared radiation. Then after that, we also have microwaves, and one more we have. Actually more are there, but one more we have for communication that we use. Anybody knows which wave we use? Radio waves. Very good. Radio waves. So all of them, okay, they are found to produce what? Heat. I do not know whether you have seen or not. Okay, imagine you have a phone, right? Not imagine, you have a phone, of course. Okay, you have phone, and what you're doing with the phone? You're trying to communicate, okay, using the antenna, and the antenna will produce waves. No, the waves which these antennas they produce is which waves? Radio waves. Okay, for communication. Yeah. Okay, what do you think? The radio waves, as they pass, right? As they pass, okay, they also produce what? They produce heat. Not only with radio waves, it is also true for microwaves. Microwaves, so obviously very easy concept, no? Okay, so you have a microwave oven. You put chicken here. Okay, this is my diagram of chicken. Okay, we are trying to cook it. So what happens? Do we need air inside? Not necessary, right? We don't need what? Air inside this microwave oven. Okay, because radiation, which is your microwaves, which is a wave, is going to hit, okay, whatever you want to cook or whatever you want to heat, and these waves only, they produce what? They produce heat on anything which they fall onto. Okay, infrared, basically you already understand, right? Infrared, obviously, right? Infrared have another name also, we call them heat radiations. Okay, visible light also. Okay, then what else? We have ultraviolet. We also have what? X-rays and gamma rays. They all are known to produce. Okay, now the idea is this. Okay, do you agree that this is the fastest mode of transfer or not? I want to transfer heat. Which is the fastest mode? Radiation. Why? Because the speed at which light travels is what? Speed. 10 to the power how much? 3 to the power 8 meters per. Light travels so fast, and with light, heat also travels so fast. So I want to transfer heat. Fastest mode is use radiations. Okay, use all the radiations that I've given you the example of. Okay, then yes, and of course, please don't forget, we don't need what? Any movement between what and what? And we don't need any medium. Yes, we don't need any intervening medium. Okay, we don't need to do that. We don't need to have any molecules in between. Okay, and there should not be there's no need for movement of what and what? Source and the receiver. We don't need to have that. Okay, the sun doesn't have to move and earth doesn't have to move. Okay, imagine, okay, this is the sun and this is earth in contact. What do you think? What is the mode of transfer in contact? Also more.
Conduction.
Conduction, okay. Imagine, okay, very bad example I'm giving you right now, okay, very bad, okay. Imagine many sun, okay, are roaming and hitting the earth. What kind of mode of transfer is this? Many sun, many sun, okay, very bad example I know, okay. Many sun are just moving here and there and hitting the earth. What is this mode of transfer? Convection.
Convection.
And yeah, okay, and finally just the light coming from sun to earth. Okay, so we have radiation. That's what we have learned. Okay, yeah, okay. There are a few things which radiation is very nice, okay, because you know what, in radiation, no, you can control the direction. Do you agree or not? Direction of heat transfer. Can you control the direction of transfer in radiation? Yes or no? Easy, no? Just take the light, and you want the light to go from which point? Energy, heat want to transfer from A to where? B. So you have some direction, no? So you throw the light from where to where?
A to B.
A to B, okay. So you have some direction, right, in which you can talk about. And you know what, this radiation, because light obeys what? Laws of reflection, yes or no? Laws of reflection. So when light falls onto any reflecting surface, it is reflected like that, obeys laws of reflection. Even your heat will follow laws of reflection. Now, do you agree or not? If you throw heat in this direction onto something, right, then it will reflect heat also in this direction. Do you agree with this? Light is reflected, so heat is also, or heat can also be what? Reflected. Okay, so light obeys laws of reflection, even heat, right, by this mode of transfer. Okay, that is radiation will obey that. I think this part is quite easy till now. Okay, then I don't have to talk about other things, but let's talk about natural convection. Okay, look at natural convection. Do you know what natural convection does in your daily life? Give me some idea. Natural convection. Okay, imagine you are sitting in a room. Okay, you have to have tea or coffee, no? This is coffee, okay, in this winter time. Coffee, what happens to coffee? Tell me. Does it just sit like that or become colder and colder?
Become colder.
Colder and colder and colder. And why it happens? I can tell you. See, because the air around your room, right, is at temperature, high temperature, low temperature?
Low temperature.
Low temperature. So now they will move, okay, they will move in random directions, okay. So this one of the air molecules, the green one, okay, let me just use this one. So this molecule here, what will it do? Tell me. It is at low temperature, huh? It will come and do what? Come near the coffee, hit the liquid in the coffee or the container, the mug, and what will happen to this this molecule here? What will happen? It will just stay there, or it will again move? It will come and pick up the heat, right? Yes or no? So
Yes.
now heat is transferred. Okay, heat is transferred from where to where?
Cup to the molecule.
Cup to the molecule, but the molecule doesn't stay there, again goes in some other direction. Okay, so it came from here, went there. This molecule will come, maybe go there. This molecule will come and maybe go there. But all of these molecules, when they come and touch the glass, the coffee mug, no, they're all picking up what? They're picking up
Heat.
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 So who's losing heat? The coffee mug will.
The cup.
The coffee mug or the coffee will lose heat. So this is how, right, the molecules, they will come and take away the heat from your coffee mug. Okay, all these molecules, right? So what is this process called? We'll call it convection or natural convection.
Natural.
That means the transfer of heat from one place to another place, right, without with motion of the molecules, right? So natural convection. Okay, can we have force also? What is the meaning of force? What will be the meaning of force? Easy.
So using heater.
You want to take heater or you want to take fan? You want to make it colder, no? So you blow a fan, right? Yes or no?
Yes, sir.
You blow a fan, okay, in this direction. Now all these air molecules, right, will be moving in this direction. But as they move through the coffee, right, not through the coffee, but through near the coffee, right, automatically what will happen? All these molecules will take away again the heat. Now you tell me, will it result in dropping of temperature or faster dropping of temperature?
Faster dropping.
Faster dropping of temperature, yes. Okay, and this time what will I call it? Natural or forced convection?
Force convection.
Force convention. Okay, that is what this is all about. Okay, so I am not going to talk about that. What else can I talk about? See, cooling system in automobiles, right? You know, cooling system in automobiles, engine. Your engine, right?
Yes, sir.
Of a car, right? Engine of a car, it becomes what? Very, very hot. You want to cool it down. What do? This is my diagram of engine. Okay, very bad diagram, I know, but it will work. Okay, so what do? You run a pipe near this engine, right? I don't know what to be called. Okay, and what do you have inside this pipe? Have you heard about the name? Coolant. Coolant. Yes. What do you have? You have a liquid here. I'm not talking about gases here. Okay, liquid. Radiator. Yeah, near the radiator. Very good. Okay, this is near a radiator.
Sir.
Yes. Jyotimai?
Sir, like cooling pads in laptops.
Yeah, that though is a fan. That is directly a fan. No?
Okay, sir.
Here also we have a fan actually. In the car also we have a fan, okay, which runs, no? But we also have what? Coolant. It's a liquid, okay? Jyotimai.
Yes, sir.
It's a what? What I'm saying?
Liquid.
It's a liquid, huh? It's a liquid which has this property, okay? Which, you know what? Which has a property of taking the heat, or let's say which has very high specific heat. Do you know the meaning of high specific heat? Means what? It can gain the heat, but the temperature will rise very little.
Rise very little.
Wow, rise very little. It can do that. So the heat it can absorb from the engine, okay? It will absorb the heat from the engine, keep on doing that, and without not much appreciable increase of temperature, okay? So this is also done to cool your what? The engine will be cool, right? Your engine will become colder. Why? Because the liquid or the coolant running through the these pipes near the radiator, right? Okay, it's going to take away the heat. And what is this? What do you think, guys? Is this conduction, convection, or radiation? What do I call it? I can have to call it what? Convection. This is a transfer of heat from the engine to this molecules which are actually moving, no? 1 second, okay, 1 second, huh? Moving, no? So that's why we call it convection. Are you convinced, guys? This is convection or not? Oh, hello. म ट्युसन लिँदैछु त्यहाँ पछि गरिदिन्छु त्यहाँ तेरिका तो नंबर पठाउँदा मलाई फटाफट कुन वाला मैले थाहा छैन Yes, guys. Tell me. I think you're clear with this, right? Why I'm calling it convection? Is it clear, guys? Yes. Hello.
Yes, sir.
Okay. Radiation. Okay, I don't have to talk about this. Okay, but which radiation is mostly known? Can you tell me, like for producing heat? Which one is the best one to produce heat?
Radiation.
Infrared. Okay. Heat radiations, mostly infrared. No, sorry. When I say heat radiations, right? Okay. When I say radiation means, of course, all of them. But which one is known very much to produce? What is that? Heating effects more. Don't forget, internet, not internet. What I'm saying, internet, infrared. Okay, my brain is also not working. Okay, 1 second. Okay, okay, check this one. Okay, so a few more things that we need to understand. Who are good conductors? So there are some materials which are good conductors. Good conductors of what? Heat. And there are materials which are bad conductors of what? Heat. Can you list them? Can you tell me for like who are good and who are bad? Can you give some examples?
So copper.
Copper, very good. Copper,
Gold.
aluminium, gold, somebody said. So basically you're telling me all the metals actually, right? All the metals are what? Good conductors of
Silver,
heat
sir.
Silver also, yes. Silver is the best conductor, no? Of heat
Yes, sir.
and what? Heat and electricity, huh? So you're talking about metals, right? Okay. Then what about bad conductors of heat?
Wood.
Wood,
Wood, correct.
rubber,
Plastic.
Rubber, okay, I agree. Plastic. Glass is a bad conductor of heat, okay.
Paper.
Paper, I think so, maybe he's right. What else? What else, guys? You're not telling me the best example of a bad conductor of heat. Yes. You're not telling me the worst conductor of heat. Not best. Worst conductor. Hmm. Let me just say worst, okay? But one of the very bad conductor of heat. Air. All of you have forgotten about air. What do you think? Air is a good conductor or not so good conductor?
Not so good.
No, not so good
No.
conductor, okay? So air also we have in this list, huh? Don't think air is a very good conductor of heat. No, air is not such a good conductor of heat, okay? Then let's quick look at this, okay? There are some daily advantages, not daily advantages, what I'm saying, daily applications of this, what we are talking about. Okay. Cooking utensils, okay? What kind of handles are provided? Tell me. Wooden handles or
Plastic.
plastic handles, okay? Utensils are made of what? Not wood, of course, they are made of metals, because you want the utensils to conduct heat a lot, okay? A lot of heat you want them to conduct, right? But handles has to be given with made of wooden or plastic, because you don't want the handles to conduct very large amount of heat, otherwise, right, you will not be able to hold the container, right? Okay. So yes, I think you got the point, okay, what I'm trying to tell you, no? Then did you understand, guys, what I'm saying right now? Did I make sense?
Yes, sir.
Okay. Utensils, handles are made of wood, because you don't want the heat to be reaching your hands and all, okay? So that's what it's all about. Eskimos, okay, look at this. Eskimos, what do? They make double wall houses. They have a wall, right? But they also put what? Another wall, okay? There are two walls like that, and in between the two walls, what is present here, guys? What is this?
Air.
Air. Yes, they have two walls, and here we have air. And you know what happens? Eskimos, when they are inside, right, they have heat, no? Compared to outside, this cold. It's hot inside and outside is cold. So do you want the transfer of heat or you don't want the transfer of heat?
We don't want.
You don't want the heat to be lost, okay? So heat is trying to escape, right? But what is present? Tell me, in between.
Air.
Air is present, and air will not allow, because it's a bad conductor of heat, no? So air will not allow the heat to escape, okay? That's why we have double wall. That is what is written here, okay? Even refrigerators are provided with what? Insulated walls, because you don't want, this is a colder place again, and outside the refrigerator, what do you get? Hot, no? Right. Your refrigerator
Yes.
is cold or your room temperature is cold?
Refrigerator.
Yeah, so this is cold. This is where you put your eating stuffs, no? You want them to be cold, okay? So do you want this heat from outside, which is at higher temperature, to come inside, or you don't want that? You don't want. Otherwise it will melt, no? Okay, how will you have ice cream, no? Like that, okay? So that's why, what kind of walls do you try to prefer to give? Very well insulated walls, made of what kind of materials, guys? Made of good conductors or bad conductors? Bad conductors. Good conductors, though, heat will enter and then gone, okay? Whole refrigerator will not work, okay? So these are some examples, please check, okay? Not so difficult. Okay, I think I can go to thermal conductivity now. You will also agree now, okay? Check. I'm writing some numbers here. directly. Look at this. K for silver, K for copper, K for air. Okay, what do I mean by this is okay, I need 1 minute break, guys. 1 minute, just 1 minute.
India
1 second, huh?
vaccinations landmark with your support and your
1 second, I
efforts.
need to make one call.
Do
Coming,
complete your
in 2
vaccination
minutes.
schedule
1 minute,
and
1 minute.
continue to follow COVID approved. Just
Okay, see, I could not make the call, right? Okay, see, okay. uh, these numbers will make sense in a while, okay, but try to understand this. See, do you agree that we can always associate, right, the ability to conduct heat, okay, with the material, right? Okay, I think you agree with that, right? The ability of a material to conduct what? Heat. Okay, how much heat it can conduct. Okay, we can always give it a number like we have given for silver here. It's not that we have given it. Okay, these are the property of silver. Okay, 406, 385 and 0 point. Look at air, look at the value of air. Okay, 0.024. okay, these numbers I told you, okay, will make a sense in a while, but try to understand. Okay, any material which is a very high value of K, I'll tell you what is this K. If it has a very high value of K, means what? It is a conductor or a good conductor of heat. First of all, that
Good conductor.
good conductor of
Good conductor.
heat. Okay, you have learned these numbers we always put, okay, as coefficients, no? So this has a name. Let me come back here. We call it coefficient of what? Thermal conductivity of solids. And basically this number tells you directly, okay, whether that conductor, that solid is a good conductor or a bad conductor. If somebody comes and tells you, okay, conductivity for such a material called X is 0, what does it mean? It conducts it or does not conduct it? Does
Does not conduct.
heat at all. Very, very important property. Just imagine. Very nice, no? Some there's an object which does not conduct heat and all. So it will be useful or very useful. What do you think?
Very useful.
Okay, who will use it? Think now. K equal to 0, or let's say K equal to low value, very low value. Who will use it? Those Eskimos will use it, no? Yes or no?
Yes, sir.
Between the walls of their houses that they build, igloo, no, they used to make. Okay, who else will use them? Refrigerator, right?
Then
While making,
refrigerator.
yes, they will come and make the walls of this refrigerator using this material, because conductivity is 0. Just imagine. Okay, so they will not use which one? What do you think? Will you make a silver refrigerator? Spaceships also very nice. Spaceships also, yes. But why did you say that? Somebody said spaceship. Yes. Abhijit Paul saying spaceship. Tell us, sir.
Space, the temperature is very low, right?
Temperature is low. Okay, agreed. Yes.
So we can use it the same way as Eskimos use it.
Okay, fine. Okay, agreed to whatever he's saying. Okay, let's agree to him. Okay. So we will not use copper, silver in space, because the heat from inside will easily escape if we do that. Okay, so that's the point, but let's try to understand it better now, why these numbers are like that and what do they mean. Okay, now let's go to this. First of all, see, you will understand, don't worry about this. Okay, see, I'll only talk about this today. Okay, then I'll stop. See, yeah, suppose I take a solid. This is a solid. It is a rectangular bar. Rectangular bar means, I think you can understand what does it mean. It's not a cube. Okay, cuboid, you can just say it's a cuboid right now. And I'm going to list some area here. Okay, the area is A here. This face of this cuboid has how much area, guys? How much is this area? A. And there's an opposite face. Okay, check, this is the opposite face. I think you can understand what do I mean by opposite face, right? Is it okay, just guys? What is the meaning of opposite phase?
Yes, sir.
Okay. How far is this opposite phase? Let's try to understand that also. How far is the opposite phase, guys?
Delta X.
Delta x. That's the distance between the phase called x and the phase called y. Okay. So they are at such a distance. Okay. Then, yes, they have temperature difference also. Let me write down the temperature difference. Okay. The first phase that I have on the left, that is phase x, has a temperature of T plus delta T, and the other phase, okay, has a temperature of T. So this is low temperature and this is high temperature. Okay. So now, do you agree that heat will be transferred or not? From which phase to which phase, guys? From phase x to which phase? Y. Okay. Let's call that heat that will be transferred as delta Q. Let's be clear. Okay. Do you understand what is the meaning of delta Q, guys? When I say transfer of heat means amount of energy, so I'm calling it Q. What will be the units to measure, guys? Can be used calories, or you can also use what? Joules. Okay. So this will tell us, no, how much heat energy is transferred from which phase to which phase? Phase x to y. You can also understand that phase x is at higher temperature, it's hot, and this is cold, so heat will be transferred. How much heat will be transferred? We are calling it delta Q. Okay. Now we also have to keep a track of the time, right? So let's call it delta T. Small t is the time. Can you understand, guys, what is small t or delta T? Time for which you are allowing this transfer of heat. It's not that you'll keep it in forever and then you measure the Q. No. We also have to keep track of what, guys? Time. And you can easily tell me, okay, if the time is large, how much heat will be transferred, more or less, in a lot of time? More heat will be transferred. Okay. So I'm going to write some formulas. Okay. Check whether it makes sense or not. Okay. See. So this is the, what is this? Now read. What is this? Is this heat or the rate of transfer of heat? Rate of transfer of heat. How much heat is transferred per second or per minute or per hour? Okay. Do you agree? Depends on the area. Okay. You take small area, and you take big areas like that. You want the heat to be transferred from here to here, and you want the heat to be transferred from here to here. Number one case, number two case. Where do you think more amount of heat will be transferred? When we take small area or big area?
Small area.
Small area? Think. You want heat to be transferred.
It's a big area.
Big area. More heat will be transferred in second case compared to which one? The first case. I'll give you an example. Okay, Jonshika, just check. Okay, say you have burned, what you have burned? You have burned charcoal, no? At home. Okay, suppose, huh? Or you are near fire. Okay, near fire. Check this example. Okay, you want to receive heat from this, right? Okay, so you will put your hands, right? Will you put your hands like this? Wait a minute. Okay, very bad diagram like that. Okay, but it will work for the time being. Will you put your hands like this, or you will try to spread out your fingers also? How do you put?
Spread out.
Yes. When you want the heat, you want the heat to be coming, right, to your hands. So what will you do? You will not keep, okay, and give a very small area exposed to the heat, right? You will try to, okay, very bad diagram I have drawn. Now your hands look like an alien, okay, but it will work, no? So, but do you understand my example, guys? What I'm trying to say? How can you transfer more heat from here to there? By having the same area or bigger area?
Bigger area.
Bigger area, yes. Okay, so that's why it's the first thing I've written here. See, the amount of transfer of heat depends on what?
Area.
Okay, it's rate of transfer of heat. Okay, then do you also agree that rate of transfer of heat will depend on the temperature difference or not? Delta T represents the temperature difference. Okay, because the temperature of this I've taken T plus delta T, and the temperature of this I've taken T. So what's the difference in temperature, guys? Delta T. Okay, imagine this is at 10 degrees Celsius, this is at 10 degrees Celsius. Is there difference in temperature? No difference in temperature.
No difference.
No difference. So what do you think? Will the heat be transferred or not transferred?
Not transferred.
Delta Q will be 0. No transfer of heat because they are same temperature. But if I start having this temperature difference, this is 100 degrees Celsius and this is 10 degrees Celsius. Now tell me, transfer of heat will take place or not? Yes. Now it will not be equal to 0. Heat will be transferred from hotter temperature body to the lower temperature. Let me give you another example very quickly, okay? Another instance. Now tell me, okay, if the temperature is 110 degree, heat will be transferred, but the temperature, if it is not 100 but let's say 1000 degrees, and that is 10 degrees, okay? Now tell me, is the temperature difference same or much bigger temperature difference? This is a much bigger temperature difference, and heat will be transferred, a lot of heat will be transferred now. Yes, I think you can make out. Okay, because of the temperature difference, right? When there's a more temperature difference, more amount of heat will be transferred. So is it okay, guys, with A and B? Just check, ask yourself. Heat transfer depends on, rate of transfer of heat depends on area. That's what you have learned. And also what, guys? Rate of transfer of heat depends on
in temperature.
Temperature or temperature difference?
Temperature difference.
Temperature difference. Don't call it temperature. Temperature difference. One more thing, okay? You'll also agree, okay? With these two phases that we are talking about, I have this phase, I have this phase. This is the distance between them. I'm calling it delta x. And imagine another case, okay? I have the same phase, but the other phase is very, very far. Now you have same delta x or bigger delta x. Number A case and B case. In B, you have a much bigger gap between the phases. Can you understand, guys, what I'm trying to tell you?
Yes, sir.
Now tell me, heat will be transferred from one phase to another phase. Heat will be transferred from one phase to another phase, right? Here also Q, here also Q, okay? Now you tell me, in both of them, same amount of heat will be transferred, or in B, less amount of heat will be transferred?
Less amount of heat will be.
Yes, because this phase and this phase are so far, so the amount of heat transferred between these two phases will be less. That means it depends on delta x or not.
Yes.
And these two phases are very near, no? Since these two phases are very near, a lot of heat will be transferred between those two phases, okay? So tell me, do you agree with this one? The rate of transfer of heat from one phase to another phase depends on the distance, or inversely depends on the distance between the phases? Inversely. More is the distance, less heat transferred. Less is the distance, more is the heat transfer. Inversely proportional, okay? Now we one more thing which we have we don't have in the formula till now, and you will agree with me, okay, on that. Say you'll agree with me on that heat transfer, does it depend on this? Yes, you agreed, okay, but also depends on what?
The material.
Okay, but you know the problem, right? We cannot put a material directly, no? We cannot say delta Q by delta T is proportional to what? Material. We cannot do that because material is not a number. We cannot do that, okay? So we should come and what? Replace some kind of number which will represent what?
The material.
The material. And that is what I've been talking about, is known as what? Coefficient of
Thermal conductivity.
coefficient of thermal conductivity. This number will tell us whether that material is a very good conductor or a not so good conductor of heat, okay? I think you got till now, okay? Notice I've combined A, B and C, okay? All of them are rate of change of rate of transfer of heat. So this and this, okay? I've just combined that, A delta T by X, okay? So what is this? Coefficient of, after I remove the proportionality sign, okay? I don't think so I have to tell you that. Rajdeep is not audible. No. Tell me, Rajdeep. You have to switch on your mic. Rajdeep. Yes, waiting. Rajdeep, waiting. Okay, I can't hear Rajdeep, okay? Can you hear me? Can you hear me? Oh, Rajdeep can hear me. Okay, fine. So check now, okay? So let me write it down for you. I have been writing delta Q by delta T, time, okay? The rate of change of transfer, rate of transfer of heat is proportional to, I told you, area, is proportional to area, then what else I told you? Temperature difference, I told you, is also proportional to, inversely on what? Inversely proportional to the distance between the phases. So this is what I've written. So delta Q by delta T, rate of transfer of heat, is equal to some constant, right? That's how you remove your proportionality sign with a constant. Then you write A, then you write delta T by delta X. I have a way of talking this also, This, okay, anybody can tell me what is this called?
It's like temperature gradient.
Temperature gradient. This is called temperature gradient. The change of temperature with distance. Okay, if I write change of velocity, no, change of velocity by distance, we call it what, guys? Velocity
Gradient.
gradient. Yes, the change of temperature with distance, we are going to call it temperature gradient. Okay, so this constant, right, as I told you, depends on the material. Let me remove it. We call it coefficient of thermal conductivity. So now we are ready to talk about this. Okay, so what is K from here? Can you tell me? K will be equal to what? Delta Q by delta T, right? Do you agree on this? Check. K can be equal to which one? Delta Q. Yeah,
by
delta Q. But if what is the condition? If A equals to how much?
1 unit.
And even delta T by delta X equal to how much?
1 unit.
1 unit. Okay, what does it mean? You know, it means that somebody asks you, okay, what is the meaning? What is the meaning? No, what is the meaning of K? What is the meaning of thermal conductivity? Coefficient of thermal conductivity. Your answer is what? Look at this. Thermal conductivity K represents what?
Rate of
Rate of transfer of heat. Exactly, rate of transfer of heat, provided you have kept the area to be equal to how much units?
1 unit.
And the temperature gradient is how much? 1 unit. And this value of K I told you for silver. Okay, how much was the value, right? Yeah, 406, 385 and 0.2. I'll come back to this. Okay, don't worry, I know it, right? At this point you are not getting me. Give me 2 more minutes. Okay, check, you will understand. See, this is how I am going to write again. Okay, the delta Q formula. Let me write again. Delta Q by delta T is equal to coefficient of thermal conductivity, then the transfer depends on this, and the temperature gradient. That is what we have written. I'm simply going to arrange this. Okay, so K will be equal to what? K will be equal to delta Q by delta T. Then this delta X I will write here on top. Okay, delta T I'll write below here. Okay, A I will write below there, of course. And this is what is the formula for what now, guys? For K. If I coefficient of thermal conductivity. Okay, now if I ask you the units of K will be what? Units of K will be units of Q. What is the unit of Q? Joules. Okay, unit of time, seconds. Distance, this is distance, so I'm writing meters. This is temperature. What is this? Kelvin. This is area, so meter square. Okay, joules per second, I think you'll agree, is called what? No, work done per second or energy per second is called what? Meter cancels with one of the meters, so I get what? Meter inverse, right? This is meter inverse. No, sorry, it is meter to the power 1, so it will go up and become meter inverse. And we also have Kelvin or Kelvin inverse.
Kelvin inverse.
Kelvin inverse. This is the unit of what, guys?
K.
K, coefficient of thermal conductivity. Yes. Okay, and this is the what I've been using here. Watt per meter per Kelvin. Okay. Now what is the dimension? Let's check the dimension also very quickly, then I'll come back to the numbers. Okay, see, the K dimension will be equal to what? Dimension of Q by T, dimension of X by delta T, and dimension of 1 by A. No, dimension of all of this will give us what? Dimension of coefficient of thermal conductivity. Okay, so tell me, what is the dimension of Q, guys? Q is energy. Energy has a dimension of ml square T minus 2. I think you're okay with this.
Yes, sir.
Okay, so I've written the dimension of Q. What about dimension of time? Time is, sorry, this is time. Oh yeah, T only, no? Dimension of time, this one. Time is what? This is not temperature, huh? What is this? Time. Dimension of delta X, which is length. Length L. Okay, what is this? Temperature. Dimension of temperature is not conductivity. What is this? Kelvin. Okay, you have seen no MLT, right? But today I'm writing K also. K stands for dimension of temperature. Okay, and this is obviously area, so we have L square for that. Okay, when we arrange, we are going to get this much. Okay, so I think you can understand this one, no? So what have I written, guys? This is the dimension of what? Coefficient of
Thermal conductivity.
Okay, coefficient of thermal conductivity. Now let me really talk about these numbers that I've written here. Okay, and then I'll be done. Okay, see. Okay, what does it mean? if you remember, the definition of K goes like this, okay? K is equal to delta Q by delta T. Then we have what? We have delta X by delta T, or delta temperature, or let me write just delta X like this, no problem. And one more thing we have, no? What is that, guys? 1 by area.
Yeah.
Okay, how to read it? K means heat transferred per second per unit temperature gradient, okay, per unit area, and the values are coming out like this. Okay, just give me 2 minutes, maybe you will really understand. Okay, see, let's try to understand this. Let me bring silver first of all. What is the meaning of this number? That's what I'm trying to tell you. Okay, definition, so you have to read only. Okay, no other option. So this is silver I've taken. Try to understand, huh? I am going to allow heat transfer from one of the phase to the opposite phase in silver. Okay, I'm talking silver right now. Only for how much time? Only for 1 second. How many second? 1 second. Are you clear with this? This delta T is how much? 1 second. Okay, then I am also telling you the temperature here and the temperature in this phase, they differ by exactly 1 Kelvin. Okay, how many Kelvin? 1 Kelvin. If this is 100 Kelvin, this is will be how many Kelvin? 99 Kelvin of this phase. Okay, and you know what is the gap between this? Exactly 1 meter. What is the gap between these two phases?
1 meter.
1 meter. Okay, and last part is the area of this phase and this phase, the opposite phases, is exactly how much I'm taking? 1 meter
1 meter
square. Okay, now my question to you is this. Okay, do you agree that heat will be transferred from this phase to this phase or not?
Yes, sir.
In silver, under these conditions, what are the conditions? Let's be clear. Okay, what is the condition, guys? I'm allowing the heat transfer for how many seconds?
1 second.
1 second.
Every second. If the temperature difference is exactly how many Kelvin?
1 Kelvin.
1 Kelvin between two opposite faces of silver, where the area I have taken for the opposite faces is exactly 1 meter square, and they're separated by 1 meter, right? Then the transfer of heat will be exactly Q equals to, you know how much? 406 joules. Can you understand this number? So please tell me, what is this? 406. It is the amount of
heat transfer.
from one phase of silver to the opposite phase, exactly in how many seconds?
1 second.
Means per second. This is like the rate of transfer of heat, only 1 second, right? If I take silver faces which have 1 meter square area and which have a separation of exactly 1 meter, and those two have to have a temperature difference of how much? 1 Kelvin.
1 Kelvin.
Okay, now we do the same thing. Okay, it's a standard way, no, of categorizing, right? Which is a better conductor, which is a not so good conductor. I'm going to take now copper. Look at this. I do the same thing with copper. What's the temperature of one phase? 100 Kelvin. What is the temperature of the opposite phase? 99 Kelvin. What is the gap between the two phases? 1 meter. How much time I allow this heat to transfer? Exactly how much? 1 second. Now you tell me, heat will be transferred or not? Did I make anything? Oh yeah, I missed. 1 meter square is the area, right? So look at this and look at this. They are identical situations or not?
Yes, sir.
Okay, the only difference is what? The only difference is what?
The material.
The material, and this material is copper, and copper is found to transfer heat not equal to 406 joules. Under these conditions, copper is found to transfer a heat of how much?
385 joules.
385 joules between its opposite faces. Can you understand? Now can you tell me who is a better conductor?
Silver.
Silver, because under this condition, which are identical situations, right? The silver is going to conduct more, is going to transfer more amount of heat. I think this part is clear, right, guys, for all of you?
Yes, sir.
Okay.
Yes.
Okay. For air, let me just compare to you with the air value also. Look at the value of air. 0. How much? 0.024. Very little amount of heat is transferred if I just compare it with these two and with air. Okay. So 1 second. Hello. Hello, bol ha. पुराना जो टेबल नहीं था सेम वाला बना, ठीक है? नहीं 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 नहीं, पूरा लिखना पड़ेगा इसमें, लेकिन हाँ अझै एड राइट क्लिक दबाएर एड रोज टेबलको भित्र राइट क्लिक दबाएर इन्सर्ट पनि हुन्छ राख्नु पछि बन्द गर्छु ट्युसन लिँदैछु okay, now we really need to do numericals. Okay, is it okay, guys? Can I stop and I just give you numericals? Can you do it from now? I'll send you the solution also directly. Is it okay for today? I'm really not okay, right?
Okay, sir.
Okay. For today,
Yes.
please manage for today. If you have doubts or anything, you can ask me. Whatever I've done, this notes I'll send you right now only, okay? And then I'll send you this numericals. We'll meet next day, not tomorrow. Maybe Monday, Tuesday, we'll see, okay? So I will ask you in the group, guys. When can we meet next day? Is Monday fine with you? 8 p.m.
Yes, sir.
Okay. If Monday is fine, then